Okay, thanks folks for joining, getting the live stream started. We'll get started in a few minutes. Sorry for a slight delay here for a few minutes, but we'll get things going. All right, we're on live stream as well. So I think without further ado, we have several people from Cube and Firebolt on board. Excited to get this webinar going. I think we had team from Firebolt team during our monthly community call. I think it was back in July. So we did about 15-20 minute demo of Firebolt in action with Cube, and that we followed that up with a blog post in August that Igor, you had a key role in. So it's good to follow up with the more in-depth webinar, and thank you, Luca, for joining us for this. So a couple of logistical stuff. If you haven't been part of a Zoom webinar before, if you have any questions, I encourage you to use the Q&A tab to post questions there, so it's easy to keep track of which questions have been answered and which haven't. I mean, we'll look at the chats as well, but we strongly encourage you to use a Q&A tab. We'll pause a few times during the talk to address any of the questions. I think Luca, you'll go first and speak for about 20 minutes, and we'll end with a demo. And after that, we anticipate we'll have some questions regarding Firebolt that people on the panel will be able to answer. And after that, we'll turn things over to Igor. And similarly, like Igor will end the session with the demo as well. It's a demo that I think we talked about in our blog post. And final item, sorry, I'm clearing the frog in my throat. We'll have a post-event survey that we'll be sending out after the event. So we appreciate if you can provide us with your feedback so we can do a better job next time around. So without further ado, it's my honor to welcome Luca Lovosevic. Hopefully I'm pronouncing your last name correctly, Luca. And I'll let you lead the presentation.
Thank you. All right, so welcome everyone. I'm a solution architect at Firebolt, and today with Igor, we're gonna show you, how to build data apps on top of Firebolt together with Cube. So let's get started. I'm gonna open, with this research by Google that's focused around the performance and the speed that the users are getting used to today. And this is just to show you the importance of kind of performance in analytics and overall in data space, right? We're getting spoiled by the web and mobile apps. And when we translate this into kind of customer experiences, they can be external or internal. We want to be performant, right? We want to have snappy UI. We want to have the application or a dashboard really perform well. And this, this translates into your standard BI solutions dashboards, but even more so into data apps. So what are data apps? Data apps are, you can think about them as a mix or a marriage between your, mobile or web applications and dashboards and visualization tools, right? It's kind of a seamless UI, seamless experience for a user, where users can slice and dice large portions of data in an intuitive way, right? So you want this experience to be kind of fast, to be robust, to handle concurrency, and basically kind of have this mobile or web-like experience. These data apps are usually built by software teams. They are delivered as your traditional applications. So when you compare it to something like embedded analytics, which is built usually by BI or data analysts, it's a different way of working, right? Different way of delivering solutions. And this also has an effect on how you implement this. A couple of examples of data apps or a couple of kind of types of data applications. They can be full-fledged products. I'll show you an example in a few moments. There could be modules within an application. Think of it as maybe an ML model or a data-intensive model that's kind of infused within an existing application. But it can also be internal tooling, and we'll see in a moment. So these are just some samples, kind of screenshots, just to kind of depict your data app as a product, right? I usually think about this, the best example I have is like Google Analytics, right? Which whenever you interact with it, it's working over huge data sets. It's completely kind of immersive on top of the data that you're working on. You can do slice and dice, you can do dashboards. Basically, it's kind of all around data, right? A module can be something like this, for example, where you do kind of engagement management across different marketing channels. You can get insights from there, but then you can switch over to your kind of standard CRM or any type of other workflow. So this would be a module within an existing application. And then finally, it can be an internal tooling. So this is like a retool, right? That's built on top of an internal data set. It can be a dashboard or anything like that. So just a couple of examples there. So why are we talking about this? We feel that today, the data platforms that are out there are not best suited for the challenges that data apps bring, right? We see that the data volumes are growing. We're past the kind of gigabyte range. We're in the terabyte range, even petabyte range with some customers. And so a combination of fast growing volumes, but also the need for speed or kind of, going into that sub-second range for your analytics brings in challenges, right? That the modern or kind of, current players on the market cannot solve easily, or at least not in a cost-effective way. And so because we are all, creative, we're engineers, we try to do different trade-offs or compromises. What we've seen when talking to customers is because they have large volumes of data, they can do several things to mitigate those volumes and to kind of get to the performance they need, but then they lose some things, right? So for example, they can aggregate data into summary tables. So they lose the most granular view. They lose the raw data, right? It's also cumbersome. It's kind of lengthy. You run your pipeline, you lose some freshness of the data because as the raw data comes in, you need to run some summary jobs or pipelines to aggregate data into summary tables. Another trade-off we've seen is you just focus on smaller time windows. So you lose depth. You lose, for example, you cannot go backwards 2 years. What happened 2 years ago on this day. And this is all kind of a compromise because you cannot work on top of large data volumes. Of course, you can also accept slow dashboard and have frustrated users, or you can kind of glue together different point solutions to come to something that works. But then again, it's like engineering time, which is costly. And the kind of things or the traits that we see that users love in data apps, it's all about performance. It's all about using a well-defined data model that you can slice and dice. And it's around big data volumes. So these three things are kind of pervasive across data apps. We can also maybe add concurrency here. It's another thing to consider. But when we think about these things, and when we map it to what Firebolt offers, we believe we have a kind of a compelling solution for this. So Firebolt is a cloud data warehouse. It's a fully managed software as a service. And primarily it's built for developers and data engineers, right? We have a SQL first mindset. Everything has an API, a lot of SDK and programmatic ways to access Firebolt and to interact with it. And we're built for speed, right? Performance is our number one characteristic. We really, everything we do, we strive to be sub-second and really get good performance over large amounts of data. We have a modern cloud native architecture. I'll show this in a few slides. But basically, we're able to run different engines or computes on top of your data and decouple this. So you can have an internal BI use case working on one engine or one compute, and your, for example, customer-facing workloads working on a different compute engine, right? So you can decouple storage and compute, so you can kind of dedicate or allocate the right resources to the right jobs or use cases. When I say we're built for speed, really what we do is, it's not magic. It's going back to the roots and kind of talking about indexing. So what we do is when we ingest data into Firebolt, we index the data according to how you specify your index, right? So you have full control over that. We store the data into what's called FFF format. You don't interact with this format directly. It's something that's stored under the hood. But basically, it kind of instructs Firebolt or is the way how Firebolt actually stores data in a sorted, compressed, and indexed way. The primary index that we use is what we call a sparse index. It's not a kind of row by row index. It's something that's indexing on the range of rows, right? So we index on ranges of data. And by doing so, we are basically very effective at finding rows. So for example, in this case, there's a sample table called fact round. There's a primary index defined on a few columns, event ID, date, and customer. And so whenever you use one of these columns in your where clause, in the select statement, we're able to find these rows very efficiently. So we don't scan, full tables, full ranges of data. We basically are able to pinpoint the rows that we need and bring them over from storage into the engine. This is how we, effectively address CPU consumption, memory, etc. And this is why the solutions, using Firebolt are typically quite cost-effective. So, as I mentioned, since we're so focused on speed and performance, primary index is not the only index type that we have. We have 2 additional index types, and these are useful for analytical use cases. So in your data applications, whenever you have aggregations or anything that's kind of doing a select and grouping by certain dimensions and doing some calculations, there's an aggregating index. And if you do any sort of joins, let's say you have a star schema, this is where we have join indexes to support and to dramatically kind of enhance the speed of your solutions. An aggregating index is very similar to what other platforms call materialized views. So it is kind of a summary table, but it's one that Firebolt maintains for you automatically, right? So you define it on top of a table. You can have one or more defined, and then you basically list a set of dimensions and a set of measures. So for example, in this case, you see in the bottom left corner, we are aggregating on top of columns, game code, player code, and currency code. And we want to produce measures such as count distinct, sum, average, and so on. Now, whenever your query hits the fact round table, so your fact table, and has one of these group bys and one of these measures, the query optimizer will replace that table with the aggregating index on the fly. So you'll get data served from the aggregating index, which means it's kind of predefined or pre-calculated, which of course, again, saves CPU time and serves data much, much quicker. Whenever new data flows in, Firebolt will maintain this index for you. So basically, you would define it only once and let it live. The join index is a bit different. It's a hash table stored in memory, so in RAM of the engine. And it's used whenever you join, for example, a fact table to a dimension table. So in this case, we are creating a join index on top of the game code column, which is a join column between the fact and the dimension table. And whenever you want to fetch game studio and game currency, those will be fetched directly from memory. So again, saving time, not going to storage, but actually having the data available in memory, which is always the fastest. Just one final slide before we switch on to a demo is the decoupled storage and compute architecture and kind of the overall high-level view of Firebolt. So if we take a look at Firebolt from 100 feet, we have 3 main layers, right? On the bottom, you have the storage layer, which is currently S3, so AWS S3. This is where data resides in FFF format. Whenever you do an insert into a Firebolt table, the data will be transformed into this format and kept in storage under the hood. And of course, apart from the data, you also have the indexes here as well. On top of this, you have kind of the computing layer. These are Firebolt engines. These are your query engines. And this is whenever you issue a query needs to hit one of the engine endpoints, basically to execute on top of your data. You can have one or more running at the same time. There are compute engines which are specialized for ingest and read. So these are like general purpose engines, and other ones which are only read-only basically, or analytics engines. And then there's a variety of sizes. So you don't go from like small, medium, large. there's really a large number of different instances that you can use. And this depends on your workload type, on your data size, query intensity, concurrency requirements, etc. And then on top, there's like the services layer, so administration, metadata, UI, and then all of the ecosystem or tools that interact with Firebolt, and then Cube being here as well. All right, so let's switch to a quick demo of Firebolt. And this will be contextual because it will be on top of the Wikipedia dataset that Igor is going to show you in a minute. Just to show you quickly the Firebolt UI. This is the main way you interact with Firebolt from like a user interface perspective. There's a database here on the left side, some scripts that I have saved. And then on the right side, you would see the tables, everything that's available to you as a user, right? In the middle pane, you have your query editor, and then the results come below. All right, so I have my database selected here. It's the BM Cube integration. I have my engine that's currently running. You can see it green here. And so let's see what we have in this database. If I do a show tables and remove external tables, you'll see I have 4 different tables within Firebolt. There's 3 fact tables, 1 dimension table. These are like different types of tables that you can create, and it affects the way the data is sharded across the nodes in a multi-node engine. We can talk about it in a minute. And then just to show you the number of rows and kind of the size of the data here. So we're talking for this demo kind of billions of rows, right? Let's say this table has 90 billion. The size within Firebolt is 250 gigs. And then uncompressed before it was ingested into Firebolt, almost a terabyte, right? So you can see that there's also a compression that's being done because we sort the data. Of course, we're a columnar database. We sort and compress the data, and this gives us some nice compression ratios as well. If I do a simple query like this one, so I'm selecting, like, just give me, 100 records that match this simple predicate. We have a log date and some Wikipedia code. You can see that I get the data quite fast. If I do an explain, you can see that the primary index is being used. It's really efficient at finding the rows because we have the 2 columns that I'm querying by part of the primary index of my table. And currently, because it's a large table, I'm basically consuming 0%. This would be something like 0 point something something, right? But you can see that we're quite efficient at finding data. Next, what I want to show you is if I do something like a aggregation. So here I'm taking a couple of days. I'm grouping by the client. Client is like a mobile or desktop. And then I'm summing the daily totals, basically the number of page views across the days. So if I do this, you can see that out of the 250 gigs, I'm really scanning a very small portion of the data. And this is like kilobytes, right? So again, if I do an explain, you'll see why this happens. What's the magic? It's basically an aggregating index that's defined on top of my page views table. So in this scenario, I'm doing a kind of a group by client. And because I have an index that's covering this, a combination of my client dimension and the sum of daily total, the measure, basically Firebolt will replace the kind of query or the underlying table on the fly and serve data from the index. Again, the index is much smaller than my original table. You can see the size of the index is quite small, right? And that's why the query is so efficient. This helps with concurrency, of course, because it's less CPU time that needs to be spent in searching the data. And so it affects performance in data app scenarios. Just one more thing I want to show you here before we switch to Igor is if I do the same query with setting this flag to 0, this flag basically says to Firebolt, don't use the aggregating index. Let's see how the query performs now. So we have our first original query. And you can see that it's scanning a much larger portion of data, right? So it's still quite fast, but it's scanning larger amounts of data. It's consuming more CPU. And compared to our original query, it's not as efficient. Again, if I do an explain here just to show you, you'll see that we're now basically going to our page views table. And from here on, we're doing the aggregation, which is not as efficient as using a kind of predefined or pre-calculated egg index. One more thing before we close this part is the engine selection screen, which is here. You remember from our architecture, you can run one or more engines on top of Firebolt. Currently, I have just one here, but I can create as many as I want to. And you can see the kind of selection or the configuration screen here. We have engines that are optimized for CPU, for storage, for memory, and kind of a balanced engine between those things. And then for each of them, there's different sizes in terms of CPU, RAM, and storage that's available. And I can also choose the engine scale. So this is the number of nodes. I can go from like a single node engine to a multi-node, let's say a 4-node engine. This, of course, helps with concurrency, with parallelizing things. It can reflect on the ingest side or on the read side. And we usually advise in going with multi-node engines. The cost is also quite transparent. So whenever you scale the engine up or down, you can see the cost per hour. And we charge this, of course, not by the full hour, but by the uptime. So if you're running for like half an hour for this one, it's going to be $5.2. And so that's about it. Any questions,
thanks.
Ray?
Yeah, I'm just scanning through both Zoom and the YouTube live stream. Yeah, there doesn't seem to be any questions so far. I guess everything is crystal clear. Yeah, as I mentioned at the beginning, if you have any questions, feel free to type them so you don't have to wait until the Q&A section, and we can even answer them live with the help of a few panelists. And the other thing I mentioned at the beginning is the slides of this will be posted on our event page after the event. So so you don't need to furiously take notes as we go along. So the slides, the PDF version will be available. And then I guess, Igor, you're raising your hand. I was about to turn things over to you. So go ahead.
Yeah, actually, before I start my part of this presentation, I wanted to thank you, Luca, for a very thorough walkthrough Firebolt, and well, I guess some of their attendees might be typing in their questions right now, so I have the chance to ask a couple of mine. So yeah, and the first thing that I'm really interested in is that, well, Firebolt seems to be a really complex platform, right? And I wonder what is kind of the best way, or maybe a few ways to kind of dig deeper into how Firebolt works. What are the resources that are available? So
Sure.
data practitioners who wanna know more can dig in.
Yeah, definitely. So I would suggest, if you're interested, there's a very comprehensive docs page. Let me open it here, which kind of has samples. It guides you through the end-to-end of working with Firebolt, with the SQL syntax, which we tend to be kind of Postgres compliant, with all of the index types. So you get kind of an overview of that, right? There's a white paper as well on our website, which goes deeper into the actual architecture and some of the choices of how Firebolt was built. But you can also engage with us directly, right? So we as a solution architects team, we're always open to discussing, kind of interesting use cases with customers. So feel free to reach out either through the website directly. There's a link for that, or find us, on LinkedIn, Slack, whatever. Yeah.
That's cool. And another question that I have, given the variety of options that are available to select and spin on different types of warehouses, I wonder what might be the rule of thumb for selecting those data warehouses. What should I start with, and what should be my approach? Maybe doing some binary search, in the available options, or something else, to pick the right one.
So there's a memory optimized engine that comes with you. Whenever you create a new database, there's kind of a predefined engine. We feel that for kind of playing around with the platform, getting the look and feel, and getting used to it, that should be good enough. Of course, there's guidance here in the docs as well on how to choose specific engines and when. If I go here, I can just quickly describe, like, for different classes of engines, the ones that are CPU optimized, we usually have very good performance and concurrency with them. The ones that are optimized for storage is whenever you want to kind of cache or keep warm large amounts of data, you can see that the cache, so the local SSD, goes to really large volumes. The ones that are memory optimized, usually good for ingestion workloads or complex queries, like the dreaded, fact-to-fact joins, which really are not the perfect match for any database, but having good amounts of memory will help there. And then balanced would be a mix. If you're really not sure, balanced is the way to go, right? Or if you're in the middle of these scenarios. It is kind of an art, choosing the good engine. But what's good here is that because of these options and because of the very transparent pricing, you're free to kind of try things and see what fits best. You can see that these kind of go gradually. So you don't need to go from like $1.3 to a $10, right? You can choose in between, and you can also choose the number of nodes to satisfy a scenario. So yeah, that would be my answer in short.
Cool. And with Ray's permission, I'll probably jump into my slides now.
Yeah, I think Luca, you probably want to stop sharing and let. Yeah. Here we go. Cool.
Awesome. Yeah. Cool. Okay. Yeah, excited to follow up with a little bit about Cube. So, I'll just start with what Cube is, and Cube is a headless BI platform, and by that by that definition, as you can see, we just really frankly claim that Cube is a kind of business intelligence platform that provides a way to deliver your data in a consistent and accessible manner to every data app, right? The kinds of data apps that Luca was recently talking about. And in a nutshell, the way Cube works is that it provide the connectivity to all the data stores out there, obviously including Firebolt, and then allows you to model your data using kind of declarative data modeling language, similar to LookML if you're familiar with Looker, but superior to it in a few ways. And then with that data modeling part, you can organize your data, into metrics definition that can be consumed by those apps, and then with a set of APIs that Cube provides, you're able to deliver those metrics to, as I said, any downstream data app, and those data apps will include front-end applications or that may be something else like data collaborative data platforms or data notebooks. It can go on and on. So here's what Cube is in a nutshell, and what we're really striving to do is to bridge the gap between their great data stores, cloud data warehouses like Firebolt, and all kinds of downstream tools and kind of data consumers out there. So you're able to build data apps using Cube as this kind of connecting piece of their modern data stack. And here's the visual way to to see how Cube fits that stack. So we are used to thinking that Cube really consists of 4 layers that does include data modeling layer and access control and caching layer and APIs, kind of matching the different functions that I've been describing on the previous slide. And then you're able to take the data from Firebolt and bring it to any downstream app and to front-end applications built with different front-end frameworks and charting libraries in particular. Let's dive deep into some of the Cube features and talk about the key ones. So one of the things that the Cube provides is consistency, and that is provided on different levels. So sitting kind of in the central place on the modern data stack, Cube is able to provide consistency of the metric definitions because it serves as a source of truth for metric definitions, right? They are not defined anywhere else other than Cube's data model, right? So you can define them there, and then they will be reused by all data apps. And then you're also able to define your access control rules in code, and those rules will be applied and enforced on all incoming queries. Queries coming from any data app out there. So you'll get consistent access control to your data, and then you're also able to declaratively, when needed, define some caching settings, and Cube will apply them to all incoming queries as well. So the consistency comes at different levels, and this is a huge part of what we are trying to provide to downstream apps. And the data modeling part, as I said, it's a huge part of Cube, and if you worked with other platforms like Looker before, you might be familiar with the style of textual representation of what kind of measures, what kind of dimensions you would like to have in your model. And well, a sneak peek into data model like Cube uses is here. So there's this concept of a cube, unsurprisingly, right? That is named, and then it can be defined over an arbitrary SQL statement that over a single table, or really over an arbitrary statement, and then you're able to define measures and dimensions in code. So this allows you to deliver those measures, dimensions, and other parts to downstream apps, and this way you're basically able to remove all the duplicated effort from downstream apps. You might be defining your data model or parts of it in BI tools, right? If you're using tools like Superset, you might be doing last mile data transformation there, but also you can move all the ways and places where you define your metrics, just upstream to Cube, and get rid of duplicated effort here. And also, which is even more important, by doing so, you'll make sure that all the data coming from Cube and consumed by different apps, that would be consistent, right? So it would be impossible to say get their number of sales last year in one app, and and kind of a different number for the same metric in another app. Let's talk about access control. So as I said, access controls are also defined in code, and here's how it looks like. You're basically able to augment any query which is incoming using some metadata about that query, and do anything with it. You can be adding additional filters. You can be completely rewriting the query, and that's managed centrally in Cube. So no downstream app, no data consumer can can do anything that would let them bypass those access control rules because they are managed by Cube. And if we talk about specifically about connecting Cube to front-end apps and using Cube's REST API, then it's worth noting that you're able not only to query Cube from the front end, but also provide the metadata. And for that API, that would be provided with, encoded as a so-called JWT, so JSON Web Tokens, which is a secure way to pass some metadata from the front end, and that metadata would be available to Cube, so you're able to do all kinds of access control with that, and probably one way to leverage that would be to deliver different data or augmented data to different users or cohorts of users, depending on what kind of metadata they supply. And another huge part of what we're trying to with Cube is to make sure that data is accessible to all kinds of downstream apps. Today we'll be focusing mostly on the REST API, which is most frequently used, in front-end apps, and GraphQL API serves that purpose very well as well. However, the connectivity options that Cube has, that they just don't stop there, right? So another option is to use a SQL API, which enables connectivity to different BI tools and data notebooks as well. The good thing is that regardless of the API choice, or you might be using all API flavors at once, you may be using just one of them. Regardless of that, you're able to declaratively query their desired set of measures and dimensions and get the same data, right? So let's talk about the REST API specifically. So the queries that you might be sending through the REST API, they look just like a very concise JSON objects that describe what is a set of measures and dimensions that you like to query. So if you look at this screenshot, you can see the gray box in the bottom, this const result set equals blah blah blah. So there you can see their list of measures that you might wanna query, and that's a query, right? So querying something from the REST API is as simple as specifying the list of measures and dimensions that you want to get. We'll talk about this in more detail later. Okay, so Luca has shown you their Firebolt warehouse that contained a lot of data from Wikipedia, specifically their page view logs from the current year, right? And what I'll show you is kind of the rest of the data built with the data, right? So you can see the architecture in the very bottom of the screen, right? So we ingested the data from an S3 bucket into Firebolt. This is what Firebolt natively supports, and then we connected a Cube instance to Firebolt. Inside the Cube instance, there's a data model defined and access control rules defined as well. And then through Cube's REST API, we are accessing the metrics defined in the data model from the front-end app built with React and the Niva charting library. Well, that could be Angular and Chart.js, or that could be just a vanilla JavaScript app, or that could even be some daemon service, just querying the data from REST API. It doesn't really matter, but the thing is that application, that demo app, well, it shows some interesting stuff from Wikipedia, and it is fast. So yeah, we have a blog post that elaborates on how that one is built. So so yeah, later if you wanna spend some some dozen minutes reading how that all was built, you can check this blog post, and also, well, you can play with the demo app on your own. And yeah, this is actually the time to take a look at how the demo app was built. And what I was going to show you is the data, how data modeling and access control work in Cube. So we'll be reviewing their deployment of Cube that's running in Cube Cloud, which is a managed platform for Cube. Also, we'll be tinkering with their end user app, right? Just to see how far the things are, and we'll review the source code for that app, so you get an insight of what kind of effort is required to integrate a front-end app with Cube. So with that, I'm stopping my slides and jumping into the next tab that I have here. Yeah, so this is a blog post, about building the same demo app. So yeah, feel free to review it if you'd like to. And here's the app. So let's talk one more time. What this app shows. So we've taken the page view logs from Wikipedia and analyzed them to determine which pages were getting the most page views compared to other pages in a 30-day sliding window. So right now you're looking at the list of their most popular pages or Wikipedia articles, and what you're able to do is to apply additional filters and see the popular articles, say on a particular date. Let's try January 2nd, or maybe 3rd, right? And what you're also able to do is to apply filters by the Wikipedia section or the language version of Wikipedia, right? So the English version of Wikipedia would be this, and then I can select a particular day, right? And then I might be switching between days. I might be switching between languages, right? And here we're looking at Wikipedia in Spanish. You can pick German, and yeah, we'll see that, well, indeed, on different days, different popular pages, and some of the days with a lot of outliers, a lot of popular pages, they are showing here. And well, sometimes they match some global events. Sometimes they match things like movie releases or some sport events or other things, and sometimes they correlate with other news. Okay, so here's how the app works, and let's see what powers this app. So I'll jump into Cube Cloud, which is a fully managed platform to deploy Cube apps. Well, it's worth noting that you're also able to self-host Cube and run it, in your data warehouse of choice. However, my preference would be to start the development and to build the POC, and then probably, just carry on hosting the Cube app in Cube Cloud, because it provides a lot of very nice developer tooling and features to monitor and scale your app and make sure that it runs just great in production. So we're looking at kubecloud, and there are a couple of interesting things here. So I'll jump into their schema section here, and yeah, I expected data schema to be in here. It looks strange. Okay, let me reload the page. Okay, so here we can see their outliers cube. I'll just do something like this. So as you can see, there's just logical grouping called outliers, right? And this cube is defined over over some SQL statement. And as you can see here, we're basically doing a union of a couple of tables in Firebolt. And not only we are reading all the data from those tables, but we're also doing some last mile data transformation here. Of course, you can probably do this with your data transformation tool of choice. If you're building, if you need, just a lot more complex data transformation, but it's totally fine, to do something like this if you want to just, extract, region code from text string or do something similar. And then you have a couple of lists, the list of measures, right? That contains just, the count measure defined, as a count of rows, and other measures that might have other counts like sum or distinct count, approximate distinct count, or average, min, max, things like that. And then you have a set of dimensions which describe the data in the table, describe your data set qualitatively, right? So these are the features in the data set. We have the Wikipedia code, the region, the URL of particular page, the title of particular page, and some other dimensions. And also we have segments in here, and segments are just predefined, I would say glorified filters that you might define, and that would help you access the data from the front end. And we also have some caching settings in here, but probably we can skip reviewing that right now. So you may wonder, okay, this is nice, but what we can do with that? And to show that, I'll just quickly jump into the Cube Playground, right? And here we can run some I would say test queries, right? Just something that we can run even before we integrated the Cube deployment with any downstream app, right? So I can do something like this. Probably select some dimension. Region is nice, and then can probably select the count measure and run this. And yeah, and probably the best way to visualize this would be to do a table, and I'll pivot it like this. Okay, this should, I want to drag and drop this. Doesn't work for me for some reason. Okay, I'll probably do it this way then. So I'll switch to table, add their dimension. Much better. Okay, so we see that a lot of page views registered for different regions, and we can see that indeed different sections of Wikipedia they get different amount of page views. That's fine. Okay, here are their segments or predefined filters. We probably wanna work only with Wikipedia page views, right? So we can narrow that down. What we also can do is maybe apply some additional filters. So say we are only interested in the page views from their English language Wikipedia, right? And yeah, and probably we can then add some more dimensions, like say the URL of a page. I guess it's the list of values here would be enormous, so I'll just limit this to 10 things. Okay. So the as you can see here, we've got a lot of other controls right in here, and yeah, we've got some data. But what I would like to show you is that if we switch to the JSON query tab, we'll see that this is the kind of the JSON representation of the query that we just basically clicked, compiled while using these controls, right? By clicking things or typing things. So this is a JSON representation, and this is a representation that you might send to the REST API and get the data back. And if you wonder, okay, but what kind of query was run against Firebolt? Well, you can obviously go to the Firebolt console and view it there, but also you can switch to their SQL tab in here and see the query. So yeah, it's not that complex. However, it's kind of non-trivial. As you can see here, what Cube does, it combines their definitions of measures and dimensions from the data schema with what's provided in the query, and creates this kind of generates their SQL query that could be ran against the data warehouse. Okay, and then well, you may wonder, okay, that's a good thing to have a look at, but how do we integrate this into with the front end app? Well, I'll just quickly jump in here and say that, well, we have the credentials for different APIs in here, and this is the endpoint for the REST API. That's the only thing needed for us to proceed in there. So yeah, let's view the source code of this front-end app and see how the data can be delivered from Cube to this app. So I have this VS Code in here, right? And yeah, I'll just leave a note that the full source code is obviously available on GitHub. So we are reviewing just what's available to you as well on GitHub, right? So the application on the front end is kind of simplistic. So it's in its HTML file, we'll just insert in this this index.js script, and that index.js script is, well, it contains just 100.5 lines of code, and well, if not my admiration for line breaks, it could have been much shorter. Okay, so you can see by comparing what we see on the screen right here with what we see right here, that is just this is just a set of React components, right? We have region selector, then we have calendar chart, we have some indicator of what's selected, and then there might be a loading indicator in there, and then there is active article list, right? And each of these React components, it just gets some data from a query run against Cube's REST API. So here's how those queries run. So this is a React app application, right? So there are a couple of packages installed. So there is this kind of core package that provides a Cube.js library, and then there is the Cube.js client package for React that provides a couple of other utilities. So basically what you need to do to fetch the data from the Cube's REST API is to instantiate the API by providing a security token and the API URL, the one that we were looking at in the Cube Cloud. And then you can wrap your whole React app with the Kube provider. That would be well, enabling any downstream React component to be able to query Kube API. And then here's what you can be doing. So this is a query which you want to run. This is basically the query that gets a list of all regions, from the Wikipedia, making sure that they are sorted, descending by their popularity, right? And then the only thing you need to do is just use this React hook with this query, and boom, you'll get result set. So when the result set is ready, you're just you're just transforming it, say by mapping, or doing some reduce or doing some other operations on the collection. You're just transforming it and setting your state variable. That's all it's needed to do, and the rest of the code is basically running different queries against the Kube REST API, getting the result, transforming it, and setting to some state variables. So you can see that if I open the network tab in here, and then I just point and click, we can see the queries running, right? So I can switch to languages. I can do more of this, and we can see the queries are running here. And yeah, you may wonder, okay, but what's the performance of those queries? And yeah, we can review that, and that would be the last part of this demo. So in the queries tab in Kube Cloud, one of the things that you can do is to review each query and what the performance was. We see that those queries, they are uncached, they are run directly against Firebolt, and here you can see the JSON definitions of the queries that were sent from the front end, right? And you can see that the duration of those queries, it's just about 200 or 300 milliseconds, way under a second. Something that you rarely expect from a cloud data warehouse. But indeed, this is how fast Firebolt is, and this is how easy it is to send a query from a front end and get some data back. Well, so with this, I'm stopping to share my screen, and I hope that was insightful, or at least not very boring.
Cool. Perfect timing too. Yeah, I think there was one question I think you've already answered about, how can somebody get started building data apps with Firebolt and Kube? And I think you kind of demonstrated that during your demo, Igor, and I think it's probably referenced in the demo app and the blog post as well, but I'll let you add you to it, Igor, and Luca, you can jump in here too. So.
Yeah, my answer would probably be just we have a great blog post. We have other both products have great docs. So I just encourage to start with the blog post and then just dive deep into them, and also feel free to join Kube's Slack community, which has about 6,000 data engineers. You can join it at slack.kube.dev, and we'll be there to help you with your data apps.
Cool, awesome. Luca, any final words? Like we're it was up here in a few seconds, but yeah,
a great demo, Igor, and Firebolt really performed there. But I love the way it's a really creative example of a real data app that someone might build. So kudos.
Cool. Yeah, look forward to seeing more from both products and both communities. So thank you, Igor and Luca, and I'm sure we'll be doing more of this in the future. So have a good rest of your day.
Thank you.